Hi, I'm Philip Brown. I'm an assistant professor in computer science at the University of Colorado, and I'm excited to share my work with you today. So at a high level, the kinds of work that my lab does deals with what I call socio-technical systems. So a socio-technical system is some kind of coupling between an engineered system and a social system. And it's the interactions between the two that kind of generate the performance that the overall system sees. So we see lots of examples of these. They're often very large, infrastructure or economy scale kinds of systems. I like to say that these things began back when eBay came along and taught us that we can use the internet to do commerce between our peers. Right? So eBay is a software platform that connects buyers and sellers together in order to do commerce. But you see this in all kinds of areas. You see this in smart grid systems where the power grid electrical distribution system is designed to be interactive with users. You see this in things like cryptocurrencies where now we are disintermediating payment networks and things like this, and in all kinds of other areas. And so the big question for engineers is, how do you design systems that have this level of social integration? These systems tend to be very large and complex. They tend to have lots of moving parts. And in many cases, I say the optimizees are themselves optimizers. So in the case of a transportation network, which we'll be talking about today, it's tempting to think about the traffic on a road as a decision variable that we can change, but it's not quite as simple as that, because each car in that traffic has a driver that has its own goals. So essentially the question is, how do we design the engineered piece on the left when the social piece is given? What kinds of challenges does this present for the engineer? So what we'll talk about today is a transportation network with self-interested drivers. And this has been studied in a wide variety of contexts. So some areas where I have some expertise, for example, are using pricing and incentive mechanisms, actual monetary incentives, to try to influence behavior on transportation networks. So here we think about charging congestion tolls on highly congested roads to try to get drivers to divert to other roads. Another area that I've looked at is self-driving car behavior design. And so in this case, we have some fraction of the vehicles are self-driving cars, and their behavior can be directly designed. And so there's a robust literature on both of these two areas that kind of considers, if you have uncertainty about how drivers are going to respond to your influence, what do you do? So today I'm going to talk about something slightly different. And so this is a new and very interesting emerging area of research, which says, let's use these kinds of models to talk about how should we provide information to drivers. So rather than directly changing people's cost functions with prices, or directly changing vehicles' behavior by designing self-driving car behavior, let's just think about, what if I provide drivers with information about the state of traffic in the transportation network? What information should I provide? And so the key question here it centers on, how are people going to process this information, and then what are they going to do with it? And so it feels like, in the kind of the intuitive sense, that if I just tell people what the travel time is on roads, that might help, right? Over congested roads that I want people to not use tend to have a high travel time. So let's give them travel time information and go from there. Unfortunately, it's not as simple as that. So it turns out in these games, if people have all the information available to them, like if everybody knows everything about the traffic state, the equilibria that arise from that are already inefficient because of congestion externalities. So what I'll be looking at today is I'll be talking about transmitting information to people about the level of congestion relative to a free flow road. So I'll tell people how much more congested their road is than it would be if there was no traffic on it. And so first, one of the questions we need to square away is, can giving this slowdown information, this information about how much slower travel is right now than normal, can giving slowdown information make equilibria worse? Right? Because if it can, we need to be very careful in how we employ this. The second, which signaling policies can minimize aggregate congestion, right? So if I pass the first bar and say, yeah, actually we can use this to improve equilibria, well then let's try to minimize worst case congestion. And then last, what are the connections to this kind of mechanism to other influencing mechanisms? So can we tie the models that we use for this back to models of altruism in self-driving cars or models of pricing in transportation networks? So I'm going to walk you through a quick toy example to show you kind of what we're thinking about. So we have a simple network with one source, one destination, and a blob of traffic. The models we look at in this paper are much more general than this. So in many of these we allow arbitrary network topologies, but for the case of, for walking you through, I want to give you this two-link network. So a blob of traffic means that we're looking at a non-atomic congestion game. So drivers are infinitesimally small and each controls an infinitesimal amount of traffic. So we'll be thinking about masses of traffic rather than discrete chunks. So the delays on the network are characterized by latency functions. So in this one, the upper latency function is linear. So if everybody is using that road, it's costly. But if nobody's using that road, it's cheap. It's a fast travel. And then the lower road is a constant latency road. So it's always slow, no matter how many people are using it. So if we have one unit of traffic and we split it half and half, then the delay on the top road is a half, delay on the bottom road is 1, and we end up with a total delay, or you could think of this as an average delay of 3/4. Turns out this is the optimal average delay on the network. Regardless of how you split the traffic, this is the best way to do it. The problem is that it's not socially stable. So the lower road has a high delay and people have an incentive to switch. So if they switch, we get what's called a Nash flow. And so this is a classic war-drop equilibrium in transportation networks, or also often called Nash flow when we have these non-atomic congestion games. And in this case, we have now all of the traffic using the upper road, which now, of course, over-congests the upper road. And we end up with a delay of 1 there. And that's everybody's delay, so that the average delay is 1. So most of the work in this area asks, how can I fix this? I have this inefficiency that's due to selfish routing. What can I do to improve this? And so let's consider the first link and ask, what is the slowdown on link 1? So how much worse is link 1 than it would be if there was no traffic? And that's just captured by this. And in this case, because it's a purely linear function, it's just equal to the delay. So the slowdown on link 2 is 0, right? The link 2 has a constant latency function. So it is no slower than it would be with nobody. So there's no slowdown on link 2. So now if I tell people the slowdown, let's think about and all people care about is the slowdown. Let's think about what might happen. Well, now there is a positive slowdown on the upper road, no slowdown on the lower road, and so you might expect people to switch all the way back to the lower road. Now this feels a little bit fanciful to say that people only care about slowdown. I know for myself, like this is purely anecdotal, I care a lot about slowdown, but I'm probably not willing to go on a road that takes 5 hours to go across town just because it's uncongested. I'm going to consider the actual delay also as well. And so what we'll do is we will model drivers as having a slowdown sensitivity, beta. And so the slowdown sensitivity will enter drivers' cost functions like this. So we're going to say that a driver experiences a cost on a road of 1 minus beta times the actual delay plus beta times the slowdown. So just a convex combination of delay and slowdown. And if you work the math out, you see this actually simplifies very nicely to just the delay minus the slowdown sensitivity times the free flow delay. Okay, so by posing the model this way, we end up with a very simple cost function that has some kind of basis in real-world decisions. I remember when I was working on my PhD and doing these kinds of models and thinking about pricing, people would constantly be asking me, "Well, I'm always taking roads that are slow just because there's no congestion on them." And so, at least anecdotally, I've found evidence in my life, and I do this myself. I've found some evidence that this is an actual cost function that some people may follow. So now, if I consider the slowdown sensitivities, and I consider what if beta equals say a half, so for beta equals 0.5, the Nash flow on this network ends up being 0.75 because the slowdown cost, the slowdown sensitive cost on the lower road is 0.5, and the slowdown sensitive cost on the upper road is 0.5 when half the traffic is using that road. And so here, this is at least a piece of evidence we can recover optimal flows by giving people slowdown information under this slowdown sensitivity model. So we may be able to improve congestion like this. So our goal now is to take this slowdown signal, like slowdown is something that we can measure, scale it by some parameter gamma, and then broadcast it to drivers. So all drivers may be different in their slowdown sensitivity, and we might not have good information about that. That might be a really difficult piece of information to obtain. So now how do we minimize congestion on the network, minimize equilibrium congestion on the network, using this gamma, this scalar on the slowdown sensitivity, given uncertainty on beta? So here's our basic model. So I'll walk you through this briefly, but obviously if you need all the details, please read the paper. I don't have the ability to go into the detail in this talk that you can if you read the paper. So we're given a network. It can be arbitrary. We'll restrict network topologies as needed as we go on. So every edge has a latency function, LE, and so for every edge, we say that the delay given on that edge is just a function of the amount of traffic using that edge, and we're going to adopt normal assumptions that latency functions are convex and increasing and monotone. So driver cost functions are given by the function I gave you earlier with this included gamma term, and so the cost function is the delay minus this scaled free flow delay. And gamma here is the strength of the signal that we're broadcasting, the strength of the slowdown signal. And beta is this driver-specific slowdown sensitivity. And so we call a flow a Nash flow. So a flow on the network is just an assignment of traffic to the various paths in the network. We call this a Nash flow. If all the beta-sensitive drivers are using path P, then that P has minimal cost. So this is just the standard definition of a Wardrop equilibrium or a Nash flow given these cost functions. So we're going to measure the cost of a flow with the total latency, and that's just the flow-weighted sum of all the edge latencies. And notice that the formula here for a Nash flow doesn't include beta and gamma. So we're measuring the actual delay when we're measuring whether or not a flow is good. We're not measuring the subjective delay that users are experiencing. And then I'm going to measure the possible harm of slowdown signaling with this quantity called the perversity index. So all we do here is we take the delay of a Nash flow under slowdown signaling, like with gamma greater than 0, and we divide that by the delay of a Nash flow with no slowdown signaling. And so here, what we're measuring, if this quantity ends up being larger than 1, that means that our slowdown signaling made things worse than if there was no slowdown signaling. But if this quantity is equal to 1 or less than 1, then that means that slowdown signaling helped. All right, so we're dividing Nash cost with signaling by Nash cost with no signaling. So our first main result mirrors some other work that we've done with pricing, and I'll talk a little bit about those connections near the end. So first, if gamma is greater than 1, then it turns out there do exist networks, pathological networks, such that the perversity index is greater than 1. So what this means is that for any gamma, I can construct a bad example that has some particular slowdown sensitivity distribution in the population and some network such that providing slowdown information actually does make for any slowdown information, even minimal slowdown information, makes congestion worse than usual. And I just realized there's an error on this slide. That should be any gamma greater than 0, not just gamma greater than 1. So this is a fairly broad negative result. However, we can put some bounds on which sorts of gammas can cause problems. So for example, if G is a parallel network, so if we're looking at a parallel network that just has a single source and single destination, and every edge latency function is this particular kind of polynomial, then I can relate the degree of the polynomial of the latency functions to the strength of the slowdown signal and guarantee that the perversity index is no greater than 1. So guarantee that slowdown signaling at least does not hurt, and actually in almost all cases it helps, as long as I'm not at one of the endpoints of this range. So I want to just walk you through very briefly a paradoxical network, one of these pathological networks, where more slowdown signaling leads to more congestion. I find these kinds of examples are a great way to illustrate the issues that arise. So notice, if you're familiar with this work, this is a Bayes paradox network. So this is a common network that's used to show pathologies in transportation networks. All right, so if we have 2 units of traffic, so our overall traffic rate is 2, and the network latency functions look like this. Let's look at the uninfluenced Nash flow. So the Nash flow with no slowdown signaling just splits the traffic half and half on those 2 paths. So the total latency now is 2, or the latency on each path is 2, and half of the traffic, one unit of traffic, is using each path. So the total latency on this network is 4 in the uninfluenced case. So now let's consider what happens if one of the units of traffic is selfish, just normal people that doesn't care at all about slowdown, so they're only latency sensitive, and one unit of traffic is very slowdown sensitive. So then the slowdown sensitive individuals, if they get the slowdown signal, will experience costs like this. And remember, the slowdown sensitive cost is just the delay minus the free flow delay. So that just recovers a cost of 0 for any of these constant latency links. So now I've labeled each of these links with the cost experienced by the 2 different populations, and let's see what happens. So in the original uninfluenced Nash flow, now the selfish traffic is experiencing a cost of 2 and can't do any better than that. But the slowdown sensitive traffic is experiencing a cost of only 1 on its link. So now they have a strong incentive to switch down to that last link at the very bottom because it has a latency of a slowdown cost of 0. And if they do that, then the selfish traffic, no matter what the selfish traffic does, it's still going to have a cost of 2. There's no way on the upper network here, the Bayes paradox network, to have a cost less than this in a Nash flow. And so now what do we have? Well, the uninfluenced case had a total latency of 4. Now the influenced case has a total latency of 5. And so we've made things worse by providing slowdown information. So this is an example of a paradox where doing something that can help in other circumstances hurts in this case. So now let's look at theorem 2. Let's focus on the case where we can actually make things better and ask how much better can we make them. So if a network is parallel and every edge latency function is linear, then it turns out we can actually leverage previous results and get some improvements. And so here we can ask which scalar, which slowdown signaling scalar gamma minimizes the worst case congestion. And it turns out if we have bounds on the slowdown sensitivities of our drivers, so we know that all drivers have a beta in some range, then we can use the endpoints of that range to compute a worst case congestion minimizing scalar. And it looks like this. And then it turns out that we can directly drop this into known results on the price of anarchy, or the worst case congestion possible on these networks, and derive some good upper bounds. And so the upper bounds are presented in the paper. They don't read very well, so I'm not going to present them here. So last, we ask, how does this relate? How do these models relate to other models of non-atomic congestion games and influencing behavior? And it turns out that there's a very deep connection, and it's driven by potential game theory. So in this model that we've considered today, if we have a particular polynomial type of latency function, so just a high degree plus a constant term, then every slowdown signaling game on this network is a weighted potential game with a convex potential function. And so what this means is that first, the set of Nash flows is non-empty and convex. And second, a Nash flow can be found using a simple gradient descent. Right? These are powerful things. Nash flows, in many cases, are hard to compute, but on these games, they're not. Right? You can find them using gradient descent on a convex function. So furthermore, we can connect a broad variety of games in this literature, both slowdown signaling, altruism games, marginal cost pricing games, and others that have a similar kind of cost function structure, and say the Nash flows on these networks with these different kinds of cost functions are identical. So if I give you a slowdown signaling game, there is an equivalent game with an equivalent population that is altruistic that has the same Nash flows. So that means we can use these potential game tools to study Nash flows on those games as well. So this is kind of a powerful result that bridges a bunch of different lines of research. So just to wrap up, I know my time is up here. The question is, if we want to provide information to drivers to improve congestion, what should we tell them? And it appears that slowdown signals might actually help, and they certainly can help on simple networks. Optimal signaling might not take too much information, and then we've provided some weighted potential gain tools for a whole bunch of different kinds of heterogeneous congestion gains, which I think is a strong new result in the literature. So I want to thank sponsors at the National Science Foundation of the US, and I hope to address any of your questions.